Yo, what's up everybody? This is your boy Kamal once again, and today we have a ridiculous looking integral here. Today we have the integral from 0 to infinity of e to the negative x times sine x times log x divided by x. So yeah, we have pretty much everything here. We have an exponential function, a trig function, a log function, and even a polynomial in the denominator. Yeah, that is pretty cool, but the question is, how on earth are we going to solve it? Well, let's invoke Euler's beautiful formula because we have a trig function here along with an exponential function. Recall that e to the ix equals cosine x plus I times sine x, which implies that the sine function, sine x equals the imaginary part of e to the I times x. And this implies we can write the target integral I as the imaginary part of the integral from 0 to infinity of e to the negative x times e to the I times x times log x divided by x dx. And now that we have two exponential functions in the numerator, we can multiply them. And in this multiplication, we have the arguments being added up. So we have the imaginary part of the integral from 0 to infinity of e to the negative x plus I times x, from which we can factor out a negative x term, leaving us with 1 minus I, times this log x term divided by x dx. It looks like we've made things substantially worse by the introduction of complex numbers. So that means we're on the right track. Now we'll adopt a Feynman's trig approach and define the integral function I of some parameter alpha as the integral from 0 to infinity of e to the negative alpha x times log x divided by x dx, where for convergence purposes, we need the real part of the alpha parameter to be positive. Okay, cool. And the reason for introducing the alpha parameter this way is if we differentiate partially with respect to alpha, the function e to the negative alpha x, then we get negative x times e to the negative alpha x. And this negative x term would cancel out quite nicely with the x term in the denominator of the integrand. And the target integral I would be the imaginary part of the integral function I of alpha when alpha equals 1 minus I. Okay, cool. So that means we have a solid plan in place, and we can now differentiate the integral function with respect to the alpha parameter. Terribly sorry about that. Meaning that on the left-hand side, we have the derivative of I with respect to alpha equal to, on switching up the order of the integration and differentiation operators, we have the integral from 0 to infinity of the partial derivative with respect to alpha because of the Leibniz rule of e to the negative alpha x times log x divided by x dx. So that means the log x by x term is a constant with respect to the alpha world, and we now have the integral from 0 to infinity of log x divided by x times, we just saw what the derivative of e to the negative alpha x is. We have a negative sign, x times e to the negative alpha x dx. Some nice cancellation taking place, and all of this implies that the derivative of I with respect to alpha equals the negative of the integral from 0 to infinity of e to the negative alpha x times log x dx. Okay, all of that was really interesting, but how on earth are we going to solve the integral of e to the negative alpha x times log x? Well, this is just a Laplace transform. Let me show you what I'm talking about. The Laplace transform of the function log x, treated as a function of the complex s parameter, is defined as the integral from 0 to infinity of e to the negative s times x times log x dx. And this thing sorts out to the negative of the Euler mascheroni constant gamma times log s divided by s. So the target integral, that is the derivative of the integral function, that's what I meant to say, is the negative of the Laplace transform with s being replaced by alpha. Okay, cool. So this implies that the derivative of I of alpha equals the negative signs canceling out, meaning that we have gamma plus log alpha divided by alpha. And now that we have the derivative completely in terms of the parameter, we can integrate to recover back the integral function. So integrating with respect to alpha gives us I of alpha on the left-hand side, and on the right we have gamma times the integral of d alpha by alpha plus the integral of log alpha by alpha d alpha. The first integration gives us gamma times log alpha, and then we have log alpha times its derivative. So that means we can apply the power rule and get log square alpha by 2 plus a constant of integration c. Now, how do we determine the constant of integration? Well, we don't. We're just going to deus ex machina this thing and call it 0 and completely ignore it. You must be thinking, what on earth is this guy saying? Isn't it a staple of my videos on using Feynman's trick to actually dedicate a section of the video to determining the constant of integration because it's an essential part of the solution development? Well, in this case, it's not. It's not important at all. Recall that the target integral I was the imaginary part of I of alpha when alpha equaled 1 minus I. So if we can prove that the imaginary part of the constant of integration is 0, that is, c is a real number, then we just don't need the value of c. Okay, cool, but how on earth are we going to prove that? Well, if alpha here is a positive real number, in that case, I of alpha, which is the integral, which in this case is the integral from 0 to infinity of a real valued function, would be a real number. So the left-hand side is a real number, and log alpha on the right-hand side would also be a real number, and that implies that c2 should be a real number. That is, the imaginary part of c is 0. So the best thing we can do here is just ignore its existence completely. Now all that's left is to evaluate the target case of alpha being equal to 1 minus I, and it would be nice to express this in the polar form. So we have the absolute value of alpha equal to root 1 plus 1, which is of course root 2. And what about the principal argument of alpha? Well, alpha equals 1 minus I, so here's the complex plane real quick. 1 unit along the positive real axis and 1 unit along the negative imaginary axis. That gives us this vector, and we have to rotate pi by 4 radians clockwise to get to the vector from the x-axis. So that means we have negative pi by 4 as the principal argument. So that means this thing equals root 2 times e to the negative I times pi by 4. And now we can easily evaluate the logarithms. So we have log alpha being log root 2 times e to the negative I times pi by 4, which using the properties of the logarithm equals log root 2 plus log e to the negative I times pi by 4, which of course gives us log root 2 minus I times pi by 4. Now we also needed the square of this logarithm, so log square alpha in our case would be the square of log root 2 minus I times pi by 4, which would give us log square root 2 plus I squared by 16. And I squared is negative 1, so that means we have negative negative pi squared by 16. Then we have the cross term, which is 2 times I pi by 4. Again, some nice cancellation taking place, so we have I times pi by 2 times the other term, log root 2. Okay, cool. Now we're interested in the imaginary parts, because I equaled the imaginary part of I of alpha when alpha equaled root 2 times e to the negative I pi by 4. Terribly sorry about that. Okay, cool. So from here, this is what we'll need. We need negative pi by 2 times log 2. And from here, we need this term. Now we had gamma times log alpha, so that means we have gamma times negative pi by 4, correct? And then we have 1/2 times log squared alpha, so that would be minus 1/2 times pi by 2 times log root 2, which means we can factor out a term of pi by 4. Negative pi by 4 factored out, leaving us with the Euler mascheroni constant plus log root 2 as the result of our target integral, which is a beautiful result indeed. I hope you enjoyed the video. I hope you learned something from the video. Be sure to like and subscribe. Do drop me a follow on Instagram as well. And in case you like the effort I'm putting out and you're learning something from the videos, if you want to support the channel, you can do so on Patreon. Thank you. See you next time.